Okay, this is one of my favorite convergence tests because you can kind of control the progress that you take here. And here's the idea. You're going to take a series that you don't know whether it converges or diverges, the original problem, and you're going to compare it with a similar looking series that you already know converges or diverges. The harmonic series, for example, or a p-series, for example, or a geometric series. Okay, things that you already know converge or diverge from some other test. And what you do is you take the ratio of those two series, okay, or the nth terms, and then you take the limit at infinity. Okay, if that ratio's limit comes out to be a positive and finite number, okay, so not zero, nothing negative, and not infinity, okay, something positive and finite, then what you get is either both series converge or both series diverge. And that's great because you already know what your series that you chose to compare it with does. Alright, very neat, very clean test, and I think you'll end up liking it as you get going with it here. So let's take a look at some examples here. Here's a series. I don't know whether it converges or diverges, and my other tests would prove to be unuseful here. This is not an alternating series. It's not a geometric series. It's not a p-series. It's not set up for the integral test, etc., etc., etc. The nth term heads to 0, so that test is inconclusive. So the limit comparison test is my next weapon here. Now, what do I want to compare this series with? Okay, what will I choose to use the limit to compare it with? Well, if I look at the leading terms here, okay, the leading terms kind of give me a hint of what I want to choose to use for comparison here. The leading terms are n squared and 3n to the fourth. Okay, so if I just think about those two terms, that'll give me a hint most times what I will compare with. Okay, so let's look at this. N squared over 3n to the fourth. If I simplify, I would get 1 over 3n squared. Okay, that is nice. Okay, because this I know converges. Okay, why does it converge? Well, n squared is a p-series with p bigger than 1. The 3 doesn't really do anything as far as convergence or divergence goes, so that just goes along for the ride. So I know this converges. Okay, and that's the keys. You got to know some things about series and some famous ones that converge or diverge, so you can use them in this test. Okay, so I know this converges, and that's what I'm going to use in my test here. Okay, so what does the test say to do? Well, it says take the limit as n goes to infinity of the ratio of your two series, and it doesn't matter which is the numerator and which is the denominator. Okay, it will not matter. So I'll do n squared minus 1 over 3n to the fourth plus 1, all divided by 1 over 3n squared. Okay, I got to calculate this limit. Let's clean it up first before we go ahead and head into the limit evaluation here. What do we really have here? I have the limit as n goes to infinity of n squared minus 1 will be multiplied by 3n squared, and the denominator will be just 3n to the fourth plus 1. Well, since I already have a 3n squared factored out, I'm going to go ahead and do the same thing in the denominator, or you could multiply out the numerators and then use L'Hopital's rule. So either way you go, I think you end up in the same place. I know you'll end up in the same place, but okay, I'll go ahead and multiply them out because that's probably what would be more comfortable for you guys. That's a 3n to the fourth. If you can't tell, I'll erase that and make it a little bit prettier for you. 3n to the fourth plus 1. Okay, and at this point you can see it's going to be infinity over infinity, and we can use L'Hopital's rule several times and get this down to, well, what are we going to get here? This 1's going to vanish eventually. This 3n squared will vanish eventually, and then these two terms are the same. So this limit's going to come out to be 1. Okay, what does that mean? Well, 1 is a positive finite number, right? Positive and finite. Therefore, this test says that both my series given and the series I chose to compare it with either converge or diverge. And since the series I chose to compare it with converges, okay, my series that I started with converges also. Why does the test work, you might be asking? Okay, well, if you think about it, what are we really doing here? we're looking at a series. We're actually looking at the nth terms of two series, and we're finding their ratio. Okay, so basically we're finding out, okay, how much bigger is one series than another at infinity. Okay, and we find out a relative size. Maybe one's double the other, maybe one's 3 times the other. In this case, they were in the same ratio. Okay, well, if they're in the same ratio, then if one converges, then the other is going to converge, and vice versa. Even if one is double the other and one converges, the other one's also going to converge. Okay, and same again goes for divergence. So we're kind of comparing what happens in the long run between two series, one of which you know whether it converges or diverges. Now, this one has a square root in it, and those are generally not favorable things to work with series. So this test comes in real handy with square roots and such. So what is my leading term? In the numerator it's a 1, and the denominator would be basically a square root of n squared. Okay, which is basically 1 over n. Okay, that's what I'm going to compare with this series with. So what does 1 over n do? I know this diverges, right? I know the series 1 over n diverges. It's the harmonic series. We talked about that last class. I think it was in the video last time for the integral test, etc. Okay, so that's what I'm going to compare with here. So what do? We do the limit as n goes to infinity. Okay, and I guess this time I'll do it the other way around. I'll put the 1 over n on in the numerator and this in the denominator. Okay, we got to evaluate this limit and see what happens here. N squared plus 1. Okay, what is this? Well, let's rewrite this a little bit. This is the limit as n goes to infinity of, in the numerator you're going to have square root n squared plus 1, and then the denominator is going to be n, but I'm going to write that as what? Square root of n squared. Okay, why the heck am I doing that? Because I want to combine these two square roots, and I actually want to put the limit on the inside of the square root. So I can use L'Hopital's rule on the inside here. Okay, we've done this a few times before, I think, putting the limit inside of a natural log or something else, and it's a convenient thing to do here. Okay, we do L'Hopital's rule twice on n squared plus 1 over n squared, and we get a limit of 1, square root of 1 being 1, and so that comes to be 1. Okay, what does this mean? Well, 1 is both positive and finite, so that means my series and this series either both converge or both diverge. And since I chose to compare with 1 over n, I know that the series given diverges. Okay, therefore, sigma 1 over the square root of n squared plus 1 diverges. Okay, and it's kind of good if they ask you to justify your answer. Obviously, you have all that work, but you can also write this little statement to kind of put icing on the cake here. By comparison with sigma 1 over n, which you know diverges. So there you go. You got an example of divergence when you use something convenient to compare with. All right, this is a good one here because there's a bunch of stuff going on. What on earth do you want to compare this with? Okay, well, you got several choices, I guess, and I'll say that you don't always have one way to do these problems here. But I'm going to ignore the n minus 1 and the n, and I'm going to focus on that 4 to the n. Okay, so I'm going to compare with 1 over 4 to the n, okay, which is a geometric series. Okay, I can rewrite it as, if I want to, 1/4 to the n, so you can see it as geometric. Okay, and this is a convergent geometric series. So I've got a series I'm going to compare it with that I know converges. Okay, convergent geometric series. Okay, so let's do our limit now. We've got the limit as n goes to infinity of n minus 1 over n times 4 to the n, all over 1 over 4 to the n. Okay, I'm going to save some time here. That's going to end up being 4 to the n over 1. The 4 to the n's cancel out, like this. Okay, and here's my limit I need to take. Limit as n goes to infinity of n minus 1 over n. L'Hopital's rule one time will tell us that that limit is 1. 1 is both positive and finite. What does that mean? It means that my given series and the one I chose to compare it with either both converge or both diverge. In this case, they both converge. Okay, so if you choose the right series to compare with, these problems can be very, very fast and clean and efficient. Okay, and through some repetition, I think you'll get pretty good at this. Okay, converges by comparison with 1 over 4 to the n. You guys are almost done with the convergence tests. Okay, so I hope that once you get them organized in your mind, you don't feel it's too cumbersome.